Okay, hope everything is fine. Okay, just let me check that everything is fine once again and we can start. Yeah, can you hear me? Can you see me?
Yeah, we can hear you, but we can't see you. But it's not a problem, I think.
Well, it was fine 8 minutes ago.
No, but we can see your screen.
Okay, yeah, that's more important, I think. Okay, so let's continue. So today we will discuss conditional expected values, conditional variance. So let's start with conditional expected value, conditional variance. And I like hear very much questions from London external exam. Sometimes I dislike them, but for this topic, I think they are fine. And let me, so I will post in the Telegram the question we will discuss. So I have sent the whole archive with all the problems I have. Maybe some new problems are missing, but all the problems are there. Okay, and let's solve this task. Ta-da-dum. Let me send the file. Yeah, here it is. Why it takes so long to upload? Okay, so it will. Yeah, here it is. Okay. They like to introduce many sources of randomness in the problem. And basically, there are two like sources of randomness they like to introduce in exam questions. The first one is random choice, random choice of a random variable. Random choice of a random variable, something like you have the random variable x1, you have the random variable x2, and you randomly are taking either x1 with probability p or x2 with probability 1 minus p, and the resulting random variable is x. Yeah. And you can ask some properties of this random variable x, its expected value, its variance, blah, blah, blah. Okay, and the other popular source of randomness in the London external exam questions is the random number of terms in a sum. Random number of terms in a sum. So you have a sum S, you sum up x1, x2, x3, blah, 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 xn, but this n is a random variable. And you study some properties of this S, like the expected value of S, variance of S, some probability is related to S. So the question is about, some properties of X. Here the question is about some properties of S. Not necessarily expected value, but expected value is the simplest property of a random variable. Okay. And let's consider an example of a question, because in almost every exam you have either the first source of randomness, either the second one, either both of them. So it's very frequent. And we will discuss how to calculate conditional expected values, conditional variance. I think for these examples, it's a very appropriate problem type. Okay, so let's consider problem 4. And problem 4 that I have sent in the chat, but I will quickly state necessary assumptions. Okay, we have n, the number of questions in the exam. the number of questions. And probably you already can guess that n will be random. Yeah, n will be constant in the beginning of the problem, and at the end of the problem, n will be random. And each question, either you know the answer or you don't know the answer. So either for each question, you know the answer with probability 0.7. 0.7, you know the answer. And with probability 0.3, you guess, I think. Yeah, you guess. You guess. And each question, and each question has, you have 3 multiple choices, three choices, 3 options. Let's say 3 options for each question. For each question. Okay. So point A is very easy. I think that's just a warm-up. What is the probability that you will answer correctly? You will answer correctly. That's just to check that everyone gets the text of the problem. Yeah. What is the probability that you will answer the question correctly? That's very easy.
Like 0.8.
Sorry?
I suppose.
With probability 0.7, you know the answer, and so you don't guess. Yeah. And with probability 0.3, you guess. You have 3 options to guess. So what is the probability that you will answer correctly?
Can we say that this is the same as answering correct, like knowing the answer, given the fact that this is the question which is, like this conditional probability?
No. That's not conditional probability, because you can answer correctly multiple choice question when you know the answer and when you don't know the answer. So you may be just lucky, and you may know the answer. So in multiple choice questions, you may know the answer, and you may
is
just
it 1 then?
Okay, so
Is
it's
it just
0.7
because it's just really looks like 0.7, and the other, like you guess, right?
Yeah,
You
plus
guess the right answer. Then it just looks 1.
no. So you know the answer 0.7 plus 0.3 times 1/3. Yeah. So you know the answer, plus you don't know the answer, but you need to have luck
yeah, right,
if you don't know the answer. Yeah.
Yeah.
Okay.
Yeah. Yeah.
Okay. Here that this 0.7, that's you guess, and that is you are lucky. So, and in both situations, you have answered correctly. Okay, now point B. First, let's. So B is about conditional probability. Let's say n is equal to 3. So n is not random. So n is not random yet. but it will be a little bit later. And the question is very simple. Given that you have answered all questions correctly, what is the probability that you know the answer to exactly one question? Yeah. What is the probability you know just one question? Given that you have answered 3 questions correctly. And as we see, given that, yeah, that means conditional probability. Given that, if and here we should obviously use the formula P A cap B divided by PB. So in this case, that's a probability that we answer 3 questions correctly. And in the denominator, I have the probability that I answer 3 questions correctly. And I know only one question. Okay, so in denominator, we already know the answer is 0.7 plus 0.3 times 1/3. We multiply this value 3 times by itself because we need to answer all 3 questions correctly. And in the numerator, we have like binomial distribution, yeah, because we need to know one question out of 3 questions. So we have choose one out of 3. Yeah, we need, there are 3 questions and we know one question. So either that's the first question, the second question, the third question, and we multiply. We need to know this question. So it happens with probability 0.7. And we need to be lucky. Hence, we have 0.3 times 1/3 squared. So it's similar to binomial distribution. In pure binomial distribution, you have choose k out of n times p power k 1 minus p power n minus k. In this case, it's a little bit different because we should be lucky. Not only we should be ignorant for 2 questions, but we should be lucky there. Okay, so it's similar to binomial distribution, but it's not like pure binomial distribution, similar to binomial. Okay, any questions there? Shall we continue? Or we are stuck?
I think yes, we can continue.
Okay, now see, we have new source of randomness, t, the time to answer a particular question, t. We have 2 possibilities for the density function. Either it's lambda times exponent of minus lambda t, if you know the answer, and 5 lambda exponent minus 5 lambda t, if you guess. So you may write the the density function like this, you have two options, yeah. Or you may say that we have a random choice of a random variable, yeah, because either this t, this time for the question, will be either equal to t1 or t2. That happens with probability 0.7. That happens with probability 0.3. T1 has, if you look at this density, probably you recognize the distribution. Yeah, what is the distribution of T1? Yeah, what is the distribution? If you have lambda times exponent minus lambda t, what's the name of the distribution? Lambda times exponent minus lambda t. The name of the distribution is
exponential.
Exponential, yeah, bingo. That's exponential distribution with rate equal to lambda. And T2 has exponential distribution with rate equal to 5 lambda. Yeah, you are right. Yeah, that's very good. Okay, how we can write it in one line? So you may write it with arrows, so you may write it with curly bracket, but we can write it just in one line. We can say that is t is equal to, we need to introduce the random variable that is responsible for the selection, for the random choice. Yeah, we may write like t is equal to I times t1 plus 1 minus I times t2. And this I is the random variable that is equal to 1 or 0. And the probabilities are 0.7. Yeah, with 0.7 we select T1, and with probability 0.3 we select T2, and I, T1, and T2 are independent. So basically, this artificial random variable I that is absent in the text of the problem, it is just the way to write the random selection. Yeah, this I, if it's 1, t is equal. So when I is equal to 1, then basically t is equal to t1. When I is 0, then basically t is equal to t2. And this random variable I, that is very simple. It takes values only 0 and 1, and it's a nice way to write the random selection instead of text. You may write a formula. Okay, what is the question? Yeah, because I haven't stated the question yet. Find, yeah, we have a lot of, find expected value of t. Find the expected value of t. And if I have this, line for this expression for t, that's random choice of a random variable, and I place the role of a switch. Yeah, it selects the random variable we need. So expected value of t, now it's a piece of cake. We just plug in what we have, 1 minus I times t2, and we are done. That's very easy because expected values are linear, and even more, for independent random variables, the expected value of a product is a product of expected values. So it's expected values of E times expected value of T1 plus expected value of 1 minus I times expected value of T2. I is a very simple random variable. I has only two values, hence expected value of this switch is, I hope, 1 times 0.7 plus 0 times 0.3, and it's 0.7. And basically we are done. If you remember, yeah, it says you can see that you can use a mean of an exponential distribution, but you need to state. Okay, if you remember well, it means that expected value of T1 is 1 over lambda. I just recap the intuition behind exponential random variable. Exponential random variable, they measure the time between arrivals of taxi cabs, between arrivals of meteors, between arrivals of student in a restaurant, and rate is how many arrivals per hour on average we have. Yeah, if we have lambda arrivals per hour on average, then the average time between arrivals is 1 divided by lambda. Yeah, the intuition is very clear here. If the rate of arrivals is lambda per hour, so if you have 2 arrivals per hour, what is the average time between arrivals? The average time between arrivals is 1/2 of an hour if you have 2 arrivals per hour. So it's very intuitive. Yeah, you may obviously integrate and obtain this answer by using integration, but basically rate is how many events, how many arrivals on average per hour, and expected value between arrivals. Okay. So here we have expected values of T2 is 1 over 5 lambdas. And basically 0.7 times 1 over lambda plus 0.3 times 1 over 5 lambdas. It will be something like 5 lambdas, 0.7. So it is 3.8 divided by 5 lambda. Okay, we are done. Hence now maybe the hardest part. We have second source of randomness. We have T1, T2, T3, Tn. And from a student viewpoint, before exam, the number of questions may be seen as a random variable. So sometimes you know that you will have exactly 20 questions in the exam, but sometimes you are told that you will have some number of questions, and from your viewpoint, the number of questions may be random. You have some beliefs, but you don't know it exactly. So it's the case of this problem. You know that expected value of n is, so I am solving the last point, C2. Expected value of n is 10, variance of n, the number of questions is 10, and the T1, T2, Tn is the random time for each question. And let's discuss the total time, W. So it's T1 plus T2 plus T3. Oops. That's my, I have a bad notation. Yeah, I have used here T1 as T1 is, that will coincide with so okay, let's say it's either, so I will change the notation here. I have not read the problem till the end. They are using T1, T2, so I will change here notation. It's either T. So it is either R1, R2, R1, R2, R1. Oh, it's I, R2. Yeah, like this. because they are using T1 and T2 later. And that's a bad idea to use the same name of random variable twice. Okay. Now, the total time for the whole exam is T1 plus T2 plus T3 plus Tn. And each of these Ti is the sum of I times R1I plus 1 minus II times R2I. So we have two sources of randomness. We have random number of terms, random number of terms, and we have random choice, of a random variable. So we have two sources of randomness. We have random number of terms. We have random choice of a random variable for every question we are trying to answer. And the question here, so let's just find expected value of W and variance of W. Okay, now let's solve it. Probably you know that expected value of W can be calculated as expected value of conditional expected value of W when you fix N. Yeah, it's called law of total expected values, or it's called Adams law, or it's called what's the name? So tower property, because it's like tower property. There are many names for this formula. And we have another formula, variance of W may be represented as expected value of conditional variance of W given N plus variance of conditional expected value of W given N. And as you guess, it's called Eve's law. Oh yeah, that's Adam's law, that's Eve's law. And why it's called Eve's law? Because if you look at the formula, you see E, V, you have once again V, E, yeah, it's maybe it's Eve, but Eve's law, like Adam and Eve. That's a mnemonic rule to remember this formula. So it's called Eve's law. Okay, so let's find this expected value of W and variance of W. The idea is very simple, basically. When you calculate expected value of W, you may fix N. So let's say that N is non-random. So how to calculate expected value of W if you fix N? We just fix N. So it's easy. We just think. So think that N is a constant. And this makes things simpler. Yeah, if we, instead of random variable n, we think that n is constant, then we are happy. Okay, let's calculate expected value of w given n. So it's expected value of t1 plus t2 plus bums plus tn, but n is fixed. Yeah, n is fixed. And if n is fixed, then we just have expected value of t1 given n plus bums plus expected value of tn when n is fixed, because the number of terms is independent of every term. So the number of questions is independent on the time you spend on each questions. So we can just omit all the n, we can omit it, yeah, and hence we have or even simpler, we have n times expected value of t1. We have already calculated it. It's n times 3.8 divided by 5 lambdas. Any questions here? Because we have used our conditional expectation for the first time during our practice. Any questions here? Okay, that's pity you are quiet, but okay, let's continue. And finally, to calculate expected value of w, we calculate expected value of conditional expected value. We calculate ordinary expected value and hence we get expected value of n, that is 10, it's given in the text of the problem, and we multiply it by 3.8 divided by 5 lambdas, it's 38 divided by 5 lambdas. Okay, and we have found expected value of w. Now let's move on to the variance. So now let's move on to the variance, and let's use this Eve's law. How to remember this formula? So probably if you are good with math, that's a good moment to prove it. If you are good with math, then you can prove it. But if you have difficulties, then you can remember it and use for problem solving. So how to remember it? Either you just recall this name Eve's law, either you consider basically two cases. So let's consider two particular cases. So my hint how to remember this formula, how to get it, probably the intuition behind it. So how to get the intuition behind this formula. The intuition, there is a geometric intuition behind this formula. Probably we will discuss it some time, 1 week or 2 weeks ago, 2 weeks in the future. But today let's discuss a very simple intuition. Let's consider two simple cases. Let's imagine then n, case 1, n is random, but every term you add is fixed, but all ti's are just equal to t. So you just add random numbers of constant. So w is t plus t plus t plus bums plus t. So and you have n terms, but every term is fixed. In this case, that is n times t, and in this case, variance of w is t squared times variance of n. And on the other extreme, case 2, if n is fixed, but ti are IID. And in this case, the variance of W, that's the variance of an ordinary sum with non-random number of terms. And it's n times variance of ti, yeah, variance of ti. And basically, these two cases are present in this formula. Because what is this? What is the first term? What is the first term? The first term, the variance of W given n is fixed, so it's n times variance of ti, yeah? So that corresponds to the to this extreme case. So variance of Wn is just the number of terms times variance of each term. What is the expected value of W given n? So the expected value of W given n is n times t, where t is the expected value of every ti. And hence the second part, this is just t squared over variance of n. And so basically these Eve's law just sum up these two extreme cases, when n is random but t is fixed, ti is fixed, or when n is fixed but ti is random, and it just sum up these two effects. So that's the intuition behind this formula, because in our case we have two sources of randomness. Every term is random and the number of terms is random, so we should apply this big formula. Okay, so let's apply it. But I think that's a good point to discuss a little bit the intuition of what each term means. So the first term is roughly responsible for the case when you think, oh, let's think n is fixed and ti is random. And the second term in the sum says, let's fix n and let's consider the randomness of every term added. Okay, now let's go to our case. What is the expected value of W given n? The expected value of W given n, we have already calculated it. It's just 38 over 5 lambdas. What is the variance of W given n? Once again, n is fixed. N is fixed. Hence, we have n times variance of every ti. That's n times variance of I1 times first R1, yeah, plus 1 minus I1 times R2. Yeah, do you remember that the time we need to answer a particular question is randomly selected between two random times. Yeah. Hence, let's calculate this value. Okay, that will be n times. That seems difficult, but in real life it's not. Okay, we have variance of I1 times R11 plus variance of 1 minus I1 times R2I. R21. Okay, are you with me? We have almost finished. I understand that the hardest part of the hardest question in the exam. So that's the hardest part of the hardest question. But let's solve it. Let's finish. I understand that should not be easy. So if you have questions, if you are lost, just say stop, and I will try to explain in other words. I'm a little bit blind without your reaction, so please tell me if I should slow down, if I should explain something, or if everything is okay, I will continue. Yeah, any questions?
No.
Okay, so let's calculate the variance of every term. What is the variance of I1 times R11? So that's expected value of I1 times R11 squared minus expected value of I1 times R11 squared. Okay, so it's expected value of I1 squared times expected value of R11 squared minus expected value of I1 times expected value of R11 squared. What do we have? We have expected value of I1 times variance of R11 plus expected value of R11 squared minus expected value of I1 times expected value of R11 squared. Yeah, and we are done. Yeah, I think we can finish. So it's 0.7 times what is the variance? That's 1 over lambda squared, because we recap that R11 is exponentially distributed with rate lambda. Hence, expected value of R11 is 1 over lambda, and variance of R11 is 1 over lambda squared. Plus 1 over lambda squared minus 0.7 times 1 over lambda squared. And we've got 1.4 minus 0.49 divided by lambda squared. And we get 0.91 over lambda squared. So that's only the first term. Yeah, that's the level of the hardest question on the external exam. I don't know of any solution simpler than this. But now the hardest point is already behind us. We just repeat the same calculations, we plug in everything. So that's the hardest point. So we will draw a happy hedgehog, because the hardest point is already in the past. We will just do the same thing with the variance of 1 minus I multiplied by R. We will obtain basically the same answer, but with different parameters, and we will plug in everything in our formula, and we will state the final answer. Basically, the hardest part of the hardest question is already solved. Okay, we have variance of 1 minus I1 times R21, and I will jump directly here. I will use analogy, and I will jump directly here. So I will get 0.3 times 1/5 lambda squared plus 1/5 lambda squared minus 0.3 1/5 lambda squared. So by analogy, everything is the same, all calculations are the same, so I will save a little bit of time and I will get 0.6 by analogy. 0.6 minus 0.09 over 25 lambda squared, and it will be 0.51 over 25 lambda squared. Yoo-hoo! And we know this, we know that, and basically what we have calculated, expected value of W given N, we know it. It's 38 over, I forgot, probably 5 lambdas.
Yep.
Yeah. Variance of W given N, I'm a little bit lazy, but it's some constant over lambda squared. So if you sum up these two terms, multiplied by N. Yeah, it's something like N times, so it's N times multiplied by N. So we have multiplied by N. That's expected value of every. No. We have multiplied by N. So it's 3.8 multiplied by N. Variance. Okay. Variance is N multiplied by some constant divided by lambda squared. And finally, we obtain variance of W. So that's the variance of the first term plus expected value of the second term. And hence we get 3.8 over 5 lambda squared times variance of N plus expected value of N times constant over lambda squared. And according to the text of the problem, this is 10, this is 10. Yeah, am I right? Yeah, they are both equal to 10. And that's the final answer. Yeah, 3.8 over 5 lambda squared times 10 plus 10 constant over lambda squared. I'm a little bit lazy. I admit that I have not finished these calculations, but we need to add this number and that number. I need to add them. It will be okay. I am a little bit lazy. Yes, but let's finish. So if I multiply by 4, I will get 2.2004 divided by 100 lambda squared. So it's 0.0204 over lambda squared. And the sum, if I sum up all these terms, I will get 0.09304, and this is 0.9304. Okay, and we're done. Any questions? Shall we go on?
Half a minute to realize what happened.
What happened? Okay, so let's go back a little bit.
I need half a minute, please. And
Half a
then
minute. Okay, I will just recap what we have done. We have W, that is a sum of random number of terms. But every TI is a randomly selected random variable. Yeah, that's the hardest point, or the hardest point of the hardest problem of the exam. Yeah, that's not easy. I agree with you. Okay, so we need to calculate expected value of W and variance of W. And we use two formulas. The first formula, that's called Adam's law or Tower property, and the second formula, variance, it's decomposed into two parts. Basically, the intuition of this decomposition, one source of variance is, so variance is decomposed intuitively into two parts. The variance provided by variance of n, given that each term is fixed, and variance provided by the randomness inside every TI when you fix the number of terms. So basically, this formula has intuitive explanation. Basically, the total variance of a sum when the number of terms is random comes from two sources. The randomness in every term you add, and the randomness in the number of terms added. Yeah, so this formula is more or less intuitive when you apply it, let's say 10 times, you will see, oh, that's intuitively clear. We have two sources of randomness inside each term and randomness in the number of terms you add. Okay, so we apply these two formulas. For these two formulas, we need to calculate conditional variance and conditional expected value. So once again, a quick overview what we have done. What is the expected value when we fix the number of terms? So n is fixed, and basically this is the expected value given n. Okay, we fix n, so we just calculate expected value of a sum. That's easy. And we get the answer for the first question, the expected value. So we apply Adam's law, we plug in expected value of n, and we are done. Now let's continue with the Eve's law. Variance is decomposed into two sources of variance. So here we have discussed the intuition. That's expected value of W given n. We have already calculated it. So now let's move on to the variance of W given n. If you fix n, so that's n times variance of every term, but every term has two sources of variance inside. So we calculate the variance of every term, and every term, the random time you need to answer a question may be either distributed exponentially with rate equal to lambda, may be distributed exponentially with rate equal to 5 lambdas. And hence, it's a little bit tough to calculate its variance, but we have done it. So here the answer, so this is n times 0.9304 divided by lambda squared. So that's the first source, the second source, they sum, and we multiply by n. Okay, and now we apply these Eve's law. we have calculated every conditional expected value, conditional variance. We plug in everything and we are done. Yeah, that's better.
Yeah, thank you very much. So it's like the first question, but a little bit more complicated, basically.
Yeah.
Could we say that the sources of randomness are the like degrees of freedom for the randomness or something? How could we interpret it, like in the very beginning?
Degrees of freedom, no. Degrees of freedom is a fixed term. That's the number of dimensions you are free to. So number of no degrees of freedom that has a special meaning. So that's the number of parameters you are free to choose, or the dimension of some space. No, but
Like I get the
some...
idea. Yeah, I get the idea with sources of randomness, but is there like a more strict interpretation of it, or that's enough?
I think that's enough. We can prove the formula. So here we have done everything rigorously with the first source of randomness, because we have a very simple notation. Yeah, we have a very simple notation. So we calculate when we deal with a random choice of random variable, we have proven everything. But when we deal with a random number of terms, we have stated the formula, but we haven't proven it rigorously. We may do so, but first let's start with some examples and let's omit the proof for the moment. I think that's not a good moment to prove the Eve's law or Adam's law. I think that's a good moment. First, let's try to apply them, and then probably we will provide proof and geometric explanation. But for the first time, for the first week, we work with these objects. Let's just apply them. But yes,
okay,
everything...
that's clear. Okay, thanks.
But yes, these formulas, we can prove it. We have enough knowledge to prove them, even in abstract setup with the sigma algebras. Okay, so let's solve some more questions from the exam. So that's exam zone A 2021 problem. But almost in every exam you have random sum, or either you either have a random sum, or either you have problem 3, either you have a random sum, either you have a random choice. So that's not specific. So honestly speaking, I have chosen two first files. In two first files, you have this type of questions. So believe me that in almost all questions, you have something like that. So that's files was sorted in, I think, historical order, just first two files. So believe me, in almost every exam you have a random sum with a random number of terms. So that's I have not chosen them specially. Yes, I have chosen the hardest questions. Yeah, yes, that's maybe if you are scared, don't be scared too much. If you look at these exams, you will see that there are easy questions. Yeah, but there are hard questions. Okay. So question number 3, I sent it in the chat. Once again, yeah, from the beginning we have a random sum. Once again, it's called W. I don't know why they prefer the name W for the sum and not S, but let it be. We have a random sum of a random number of terms. N has a Poisson distribution with mean mu. xi, every xi has every xi has a exponential distribution with rate equal to lambda. So density of every x is lambda times exponent minus lambda x, or x bigger than 0 and 0 otherwise. And all they are independent, x1, x2, bababums, and they are independent. And my first question, point A, find the moment generating function for W given n. So that's a question about the conditional expected value, because moment generating function is unconditional expected value. So conditional moment generating function is conditional expected value. Let's recall that moment generating function m of u is just expected value of exponent of w times u. So that's ordinary moment generating function. That's ordinary moment generating function. And when we speak about conditional moment generating function, so what is a moment generating function? So it's like conditional moment generating function. We fix something. We fix the number of terms. So let's remove randomness from the number of terms. So let's say that n is not distributed according to the Poisson law, but we say, oh, let's simplify the problem. Conditional MGF, so we have mw given n of u, so it's expected value of exponent of w times u given n. Yeah? So we say, oh, let's forget that n has Poisson distribution. Let's say n is constant. So here n has a Poisson distribution. And here n is constant. So that's much simpler. Yeah, we have simplified. We have removed the randomness in n. Okay, let's work out this exercise. Okay, if n is fixed, what is mw given, and we fix n, and u is a parameter. Yeah, that's hard working with the moment generating functions. Once again, that's the hardest question from the exam. I think so. So I think questions about conditional probability, question number 1, is much easier. So if you are scared, once again, don't be too scared, because we are practicing, and I have chosen the hardest questions. Okay, let's continue. We say that it's exponent of x1 times u plus x2 times u plus bababums plus xn times u, and n is fixed, n is constant, n is non-random. But if n is non-random, so we can say that it's expected value of exponent of x1 times u given n multiplied by expected value of the exponent of x2 times u given n, and so on. Yeah. Expected value of the exponent of xn u given n. Yeah, because if random variables are independent, expected value of a product is a product of expected values. So here I have used the fact for independent R1 and R2. Expected value of a product is a product of expected values if R1 and R2 are uncorrelated. They are independent, but that's more than uncorrelated. Okay, so my conclusion is that conditional moment generating function of W when we fix n is just expected value of the exponent x1 times u, and we have power n. Okay, and inside we have a moment generating function function for x1. Okay, let's calculate moment generating function for x1. That's expected value of exponent of x1 times u. Oh, we need to integrate. Oh, we have two options basically. If you remember the moment generating function for an exponential random variable, then you can just write it and say, oh, I remember because exponential distribution is very often used. So you can, if you state carefully, you state, oh, I know the expected value of the exponential distribution. Oh, I know the variance of the exponential distribution. I know the moment generating function of the exponential distribution, and so on. So exponential distribution is a known object. It's considered like a known object, and you may state results about this object without proof and use them, but I will find it so because that's not hard, and the moment generating function is rather new object to you, and it would be better to even derive it once again, even if we have derived it. Okay, so that's integral from 0 up to infinity exponent of xu multiplied by PDF lambda times exponent minus x, minus lambda x dx. Yeah, that's PDF. That's our function. We calculate the expected value. Hence, it's integral from 0 up to infinity lambda times exponent minus x times lambda minus u. Yeah, am I right? I think I'm right. Dx. When we integrate this, it will be lambda times exponent minus x lambda minus u divided by minus lambda minus u, and x goes from 0 up to infinity. I think we are done. We will have 0 minus lambda over lambda minus u, and we will have lambda minus u. So that's the moment generating function of x1. And we have conditional moment generating function of w when number of terms is fixed, and it will be lambda minus u power n. So we have conditional moment generating function. We have solved the point A. We have 4 marks. Yeah, we have 4 credits for this. Okay, let's continue. Now, I think that's the hardest part of the question. Calculate unconditional moment generating function for W. Calculate unconditional expected value of W times U. And once again, we use Adam's law or Tower property. We just say that That's expected value of conditional expected value when n is fixed. And this we have calculated. So that's expected value of lambda, lambda minus u power n. So how to calculate this expected value? We need to multiply value by probability. Yeah. If n is equal to 0, then we have lambda, lambda minus u power 0. And this happens with probability. Yeah, let's recall the Poisson distribution. We have expected value of n is mu, n has Poisson. So let's stop for the moment here. N has Poisson distribution with rate mu, and hence probability that n is equal to k is exponent minus mu multiplied by mu power k over k factorial. For example, the probability that n is equal to 0 is exponent minus mu. Probability that n is equal to 1 is exponent minus mu times mu. Probability that n is equal to 2 is exponent minus mu times mu squared over 2 factorial, and so on. Okay, that's just a short summary about Poisson distribution. And hence, let's continue. Let's calculate. I don't think that I have enough place on this page, so let's continue on the next page. I will just copy this part for simplicity. I will just copy it. Okay, and now we can continue. We just say we multiply probability that n is equal to 0 times lambda, lambda minus u power 0 plus probability that n is equal to 1 times lambda over lambda minus u power 1 plus probability that n is equal to 2 times lambda over lambda minus u power 2 plus blah, blah, blah. So that's a standard formula for the expected value. Probability times value plus probability times value plus probability times value, and so on. Hence, here we are. Exponent minus mu multiplied by 1 plus mu times lambda, lambda minus u plus mu squared over 2 factorial times lambda, lambda minus u squared plus mu cube over 3 squared times lambda, lambda minus u cube, and so on. And how to find this infinite sum? If you look carefully, you see something like, oh, I see something like 1 plus t plus t squared over 2 factorial plus t cube over 3 cube, or 3 factorial, sorry, t power 4 over 4 factorial. And if you remember, that's just the formula for the exponent of t. We just see this known formula in our expression. And hence, that's exponent of minus mu times t here is just mu times lambda divided by lambda minus u times exponent. mu times lambda over lambda minus u. And we've got the formula, exponent of mu times lambda over lambda minus u minus 1. So that's the moment generating function of W. We have solved the hardest part once again, and everything else is just anticlimax. We have reached the top of the mountain and we go down, we chill a little bit, we observe, we stop at few points, and so on. So just the end of the game. As we have moment generating function, we can move on to point C. So, but basically, that's the hardest part. We need to look at this formula and recognize the Taylor expansion of the exponent function. I understand that that's not easy to see Taylor expansion, but that's the level of the hardest question in the external exam. Okay, let's move on to see how to calculate expected value of W. If you remember, expected value is just the first derivative of the moment generating function. We just take the first derivative of the moment generating function, and if we need to calculate variance of W, we need to calculate expected value of W squared minus expected value of W squared afterwards, or we can calculate expected value of W squared is just the second derivative of the moment generating function evaluated at 0. Yeah. And we can easily take the derivative. So that's the first approach to calculate expected values. So that's strategy one. So you may apply this strategy. And there is strategy 2. We have already discussed the strategy 2. Strategy 2, we can say that expected value of W, that expected value of conditional expected value of W given N. So it's expected value of N times expected value of X1. X1 has times 1 over lambda. Yeah. And we've got expected value of N times 1 over lambda, and it will be mu times 1 over lambda. So that's strategy 2. Apply. So in strategy 1, we use moment generating function to calculate moments. In strategy 2, we apply Eve's law and Adam's law once again. Yeah, to calculate variance of W, you need variance of expected value of W given N plus, or maybe it's Eve's law, so I will say expected value of variance, EV, yeah, Eve's law, variance of W given N plus variance of expected value of W given N, and it is expected value of N times variance of every term is 1 over lambda squared plus variance of N divided by lambda. And that's the strategy 2. Apply Eve's and Adam's law directly to expected value and variance and not take the derivative. But you can take the derivative of the moment generating function, as we have moment generating function calculated in the previous point. And it will be expected value of N is mu over lambda squared plus what is the variance of n. N has Poisson distribution, so it's mu 1 over lambda squared. And we are done. I think that's all, because the last question, I don't know why it's priced 6 marks, the last question, but just for the sake of completeness, I don't know why they have priced the easiest part of the question by the highest grade. I don't know why z, when it's equal to nx1, calculate expected value of z, but we have no random number of terms, we have no moment generating functions. I don't know why they have priced by 6 marks and the previous one by 5 marks. I don't get the pricing, the grading scheme. I disagree with it, but I have no votes in for the grading scheme decision. Okay, so it's expected value of n times expected value of x1, and it's mu 1 over lambda, and the variance of z is expected value of n squared x1 squared minus expected value of n times x1 and that's expected value of n squared times expected value of x1 squared, and we just finish everything we need just to complete this question from the exam. Okay, so that's variance of n plus expected value of n squared times variance of x1 plus expected value of x1 squared minus expected value of n times expected value of x1, and we multiply both terms and square them afterwards. Variance of n is mu, expected value of n is mu, variance of x1 is 1 over lambda squared plus 1 over lambda squared minus mu 1 over lambda squared, and that's all. So I don't know, I think D is easier than B and C, but it is graded higher. I don't know why. Okay, if you have any questions, don't be shy. You may ask them during my presentation. You may ask them meanwhile, in between our meetings. But that's all for today. See you next time. I strongly advise you to look through past exams. I understand that external exam is very, very far away. It's next year, but there are hard questions there sometimes, at least some of them. That's all for today. Yeah.
No, it's just I wanted to. You can say goodbye to everyone. I just wanted to stay to ask some questions.
Yeah. I have. Yeah. Oh, yes. You are free to stay. Yeah.
Okay, I have. It's just more question about notation. Do I understand correctly when we have written this moment generated function? We have
Let's go back.
min.
Should I
Yes.
go? So
No, it's fine. Like that the notation which used it was win.
the notation,
Yeah.
win, it's not. So it's W conditional. So what does it mean? So it's mean not win like a victory, but it says W given n, or W if n is fixed.
I see.
Or W if we drop randomness in n. Yeah.
Oh,
So
I see. I just was thinking maybe it's some kind of
no, that's
computation
just a
for
vertical bar. That's not I. Yeah.
vertical
Yeah.
bar. Ah,
So like in conditional expected value, PA given B.
I see.
Yeah,
I
that's
see.
a
I see.
vertical bar. Yeah. So
I
that's
see.
not I. That's not a letter. That's maybe. But don't be shy if you have notation questions. I think they should be asked immediately because they are not hard to answer. That's just, I think, 30 seconds.
I just think I'm sometimes a bit late. I'm trying to understand the previous part. Yeah, that sometimes happens to me that I ask questions a bit later.
Thank you very much for your question, because I think you are not alone. If
I just know that I sometimes can write like this, like I. It's not good, but sometimes I really do this when I'm writing titles or something like that. That is why I haven't had idea that it is. That is why I thought first that it was I. But yeah, sometimes it can be in division. And also, I had a question about like a sum from which term we go like, and
should I go that's here, or maybe could you specify where we should
yeah,
go?
I just trying to a bit remember in which part there's not clear what kind of summation we have.
We have a random number of terms.
Yeah, this is I know.
So now the
This
first
one is
question
clear.
is the global question is to calculate this. So the global question is to calculate unconditional ordinary moment generating function, but it's a little bit hard. And at the first step in the point, so that's the global target. So that's a final target. Yeah. So that's a final target. We need to calculate unconditional moment generating function. But it's hard because we have two sources of randomness. N is random, every X is random. And so we go to conditional MGF, M of W, moment generating function of W given N. So that's called moment generating.
Yeah. I remember this
function
now.
of W given N. Okay. And here N is no more random. Yeah, it's fixed. It's a constant. And if it's constant, we just use ordinary rules for ordinary product. Yeah, because that exponential of a sum, it may be written like exponential of x1 times u times exponential of x2 times u times exponential of x2 times u. Yeah, so that's the product. Expected value of a product of independent random variables is just product of expected values. So we have n identical terms in our product. So we need to calculate typical term and just use n in the exponent. Yeah, multiply it n times. So we calculate this expected value moment generating function for x1. And here we either should know the answer because exponential distribution is very, very often used. So it's better to know its expected value, its variance, its PDF, its moment generating function. Obviously, we can derive everything, but I think for exponentially distributed random variable, if you are good in math, it's better to know properties of exponential random variable. But here I derive the moment generating function for the exponential random variable. That's an expected value, but the exponential random variable is continuous, so I just integrate the PDF multiplied by exponent of x times u, and that is the result. And so I have a conditional moment generating function. That's conditional MGF. And to get unconditional MGF from conditional MGF, I just take expected value. That's Adam's law. Yeah.
Oh, yeah.
But that's not easy to calculate expected value because we have infinite sum. We have infinite sum, probability multiplied by value, probability multiplied by value, probability multiplied by value. We have infinite sum. But if we look carefully at this sum, it's a Taylor, so we recognize, so like we see, that's rabbit. Yeah, we need to recognize a rabbit by long ears. Yeah, so we recognize, oh, we have infinite series, but I don't know many formulas.
Maybe, yeah, that we see it's similar to the exponential behavior.
Yeah.
I think I also have some question about notation. Another, it's like when we discussed task 4, and you see
in previous.
Yes, it's like about conditional exponent.
Yeah.
In one we write f multiplied by n, but I didn't understand fully that was written here.
Where I should
This
go?
is a point. It's like before intuition, explanation should be. Like a bit farther. And yeah.
That's random choice of a random variable.
No, it's like when v given n. Exponential v given n. It's lower. Yeah, this one. Figure that n is a constant. Do I understand that this is like function t of t multiplied by n? Or
I don't get to.
This is which is blue ink written. Like
yeah.
there's a thing that n is a constant. Like
yeah. When we calculate expected value of w given n, it's once again vertical bar. We fix n, so we think of n as a constant. Yeah.
Yeah, I just don't get it. What is written f? Fix n. It just means a word.
Yeah.
I don't know. It's really like similar to
fix
multiplication. That is why I.
No.
I'm really sometimes not attentive. I really was thinking that it means like some kind of f multiplied by n. A bit. Yeah, I got it that like we think that n is constant. I just didn't get that it was just a fix. Yeah. Okay, I think maybe some other questions, or maybe I just need to process everything and ask later them.
Okay, but don't be shy. So
okay.
Yeah, thank you very much. Because I think that most of students, they are not as brave as you are. I think that. Thank you very much.
Yeah. I do think that I'm just really not attentive always. I'm just trying to concentrate.
The difference that you are brave. So I think that normally, we have no questions. No, why should I ask a question? Everyone is quite Oh,
Mm.
thank you very much. Thank you very much
And
indeed.
I think maybe I'm afraid that maybe will make us go slower, but maybe a bit slower.
Okay.
Maybe
Yeah.
I'm just sometimes too much to get distracted, maybe. But I just really find myself that I'm trying to get right from the previous a bit upper what we had before, like make a screenshot and
Yeah, I understand that the problem with online. I will try to think a little bit. I will
but maybe
think
that's
about
not
it.
really important because you can actually by notes understand what was previously and you might be better for that to listen.
Yeah, I will think a little bit. What can I do? Okay.
But maybe that's not important because maybe it's better to go on the same pace, so just we could do everything we can and more listen.
Mhm.
Okay.
In any case, thank you very much.
Okay, thank you also.
Yeah. Bye bye.
Bye-bye.